Good morning, good evening, whatever it might be. Mr. Bailey here, introducing you to Year 13 Differentiation for the Edexcel A-level content for maths. So this is a huge chapter. It's the second biggest after the integration, so it's hugely important, and this chapter is going to take you through lots of different results, most of which need to be memorised, but not all. I'll mention which need to be memorised and which do not as we go through these sub-chapters. Anyway, before we carry on, we need to get warmed up as ever. So I've got 4 questions for you to attempt here. So try all 4. Question 2, I've left fairly ambiguous deliberately. You show how you want to that these results are true. I'll leave that for you to decide how you want to show that these results hold. So pause the video now and attempt these 4 questions. And when you're ready to see the solutions, press play and then I'll guide you through them. And hopefully our answers will match. Okay then, so without any further ado, let's have a look together at warm-up question 1. So we need to prove from first principles that the derivative of x cubed is 3x squared. So we need to remember the definition of the derivative from first principles. So first of all, let f of x be x cubed. Then by the definition of the derivative, f dashed of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. So if we substitute in that f of x is x cubed, then f of x plus h will be x plus h all cubed, and minus f of x will be minus x cubed. So if we replace f of x plus h with what f of x plus h would actually be in terms of x and h, we have this line here, x plus h cubed, then minus f of x just minus x cubed. So if we expand these brackets out now, using either binomial expansion or otherwise, what we get, x plus h cubed becomes x cubed plus 3x squared h plus 3x h squared plus h cubed. And so all I've said here really is that x plus h cubed becomes this here. So that's all we've done at this step, just expanded out this bracket into this. But now, hopefully we can see, once we've expanded it, these x cubed at the start and the end will cancel, so we can just knock those off both sides. And then if we divide the remaining terms all by h, 3x squared h divided by h, that just leaves us with 3x squared. This divided by h will leave us with 3xh, and then h cubed divided by h will leave us with h squared. So the next line becomes this. So it's a limit as h goes towards 0 of these 3 terms. And if you notice here, the only term independent of h is 3x squared. So if h shrinks down to 0, 3x squared will always be 3x squared, but these 2 other terms, because they involve h, these 2 terms will shrink towards nothing and will vanish. And so an extra line of explanation, which is optional, we could say here that as h approaches 0, 3xh goes towards 0, as does h squared. Therefore, just to conclude, the limit f dashed of x as h approaches 0 of these 3 terms just becomes 3x squared. Therefore, f dashed of x is 3x squared. In other words, the derivative of x cubed from first principles is 3x squared. Question 2. Show for small values of h that sine h over h approximates to 1 and that cos h minus 1 all over h approximates to minus a half multiplied by h. And this needs to be where h is in radians. Okay, so sine and cos are both in radians, and h is an angle in radians. So I don't know how you proved it. I'm going to show this using a table. So here's the table. I'll start with h, for h being big, and then I'll shrink h down towards 0 as we progress. Then we'll keep an eye on the values of sine h over h, and the value of cos h minus 1 over h as h shrinks down towards 0. And as that happens, we'll keep an eye on the value of sine h over h, and we'll see if cos h minus 1 over h does get closer and closer to minus a half h. So let's start with h being 10. You can try this on your calculator. These are the values we'd get. So sine h over h is nowhere near 1 really, and minus 0.18 is nowhere near minus 5. But let's carry on. Shrink h down to 2. Sine h over h is getting closer to 1, but it's nowhere near really. Minus 0.708 has got closer to minus 1. So just keep an eye on these. I won't talk over it. I'll let you do the looking for yourself. H becomes 1. H becomes 0.5. H becomes 0.3. 0.2. 0.1. and now 0.01. So hopefully you can see here quite clearly that as h does shrink towards 0, sine h over h, you can see it's getting so close to 1 that therefore it's quite obvious that as h approaches 0, sine h over h is getting very, very close to 1. And in the same way, cos h minus 1 over h, we can see this value here is getting exactly the same as minus a half h. Minus 0.00499999 is so close to minus 0.005. You can see what's happening. It's going to become exactly the same in the limit as h goes towards 0. So we can conclude here. I think this is proven the point quite clearly. So therefore, as h goes towards 0, we can see that sine h over h is very approximately 1, and cos h minus 1 over h is a very good approximation to minus a half h. And if we continue this towards the absolute limit of h going towards 0, then in the absolute limit, sine h over h would become 1, and cos h minus 1 over h would become one and the same thing as minus a half h. Question 3. In bold it says using an algebraic method, so we can't just bang in numbers onto our class quiz, we need to think what we're doing here. Find all solutions to this equation. Well, the first thing I'd suggest is to notice that all terms have an x in. So we can factorise out an x straight away. So we can say this is x, brackets 3x squared minus 17x minus 6 equals 0. And then this bracket here will factorise as well. So in terms of factorising this quadratic, there's a few different ways in which you can factorise quadratics. This way I'm going to just put into a thought bubble over here, in case you've not seen my way before. What I'd think of this here, I'd times the 3 by the minus 6, so we get x squared minus 17x. Now think of this as being minus 18. We'll return to this 3 in a second, and then we factorise this quadratic as normal, a basic one. So we need two numbers that multiply together to give minus 18, but when we add them, we get minus 17. These two values would be positive 1 and minus 18. Then what we need to do, because that 3 disappeared, we put this 3 back in by dividing each of the constant terms in the brackets by that value. So if the fraction will simplify, we simplify it, and then if there's still a denominator remaining, we put the denominator in front of the x. So 1/3, that 3 still remains. So if we put the 3 in front of the x, we get 3x plus 1. However, 18 over 3, we can perform, that just becomes 6. So the second bracket just becomes x minus 6. And so the fully factorised version of this bracket, it becomes this here. So we can just put this in on the next line. We have x, brackets 3x plus 1, brackets x minus 6 equals 0. So therefore, we can now ask the question, what values of x would make this equal to 0? So therefore, x could be 0, looking at this first one. To make this bracket equal to 0, x would have to be minus 1/3. And this one, x would have to be positive 6. And so those are the 3 real solutions to this equation. X is 0, x is minus 1/3, or x equals 6. Question 3, we're going to use for question 4 now. So question 4, it says, using your answer to question 3, find all real solutions to this equation. So I'm just going to write up in terms of big X what we had from before from question 3. So from question 3, what we had here, if I just replace little x with big X, it was 3 big X cubed minus 17 big X minus 6 big X equals 0. We had that factorised into, let's have a look again, just to remind myself, x, 3x plus 1, then x minus 6 equals 0, and then we had our solutions whether x equals 0, minus 1/3, or 6. So I'm just going to put this to the side just as a reminder of what we did in question 3, replacing little x with big X. I'll explain why in a second. So how does this relate to question 4? Well, what we can hopefully spot here is that this big X, we could say big X is simply y minus 2 all squared. And that way, this big X, oh sorry, that was big X cubed, my mistake, and that was big X squared. So what we can say here, if we make the substitution that big X is y minus 2 all squared, then y minus 2 squared cubed would give us y minus 2 to the power 6, and y minus 2 to the power 4 will be the same as y minus 2 squared squared. So if we just say let x, big X, be y minus 2 all squared, then we have what we have here, 3x cubed minus 17x squared minus 6x equals 0. Then we can use what we had from question 3. So from question 3, solutions, x, this is going to be 0 when x is equal to 0 minus a third or 6. But what we said here is we're letting big X be y minus 2 all squared. So we want to solve this in terms of y. And so what we can say here is therefore that y minus 2 all squared is 0 minus 1/3 or 6. Now we can think about how to solve this in the right way. So what we need to do here is to think about how to make y the subject. So if I just take this step here, what we can do is square root both sides and then consider plus and minus options. So y minus 2 equals plus or minus the square root of 0 plus or minus the square root of minus a third, or plus or minus the square root of 6. Now, we can't square root in terms of being a real solution a negative value. So what we can do here is we can say this solution there is no good. Therefore, y minus 2 plus or minus the square root of 0 is always going to be 0. Then or plus or minus the square root of 6. So therefore, putting it together, add 2 to both sides. Y equals 2 minus root 6, or 2 plus the square root of 6. Those are the 3 real solutions for what y could be. So that's question 4 done, therefore, hopefully we're fully warmed up. So let's talk about today's main differentiation. So we're going to start by differentiating sin𝑥 and cos𝑥 from first principles. So what we need to do, we need to use the established small angle approximations for sine and cos when the angle is measured in radians in order to differentiate sin𝑥 and cos𝑥 from first principles. So this links back to previous chapters in year 13, trigonometry and small angles given in radians. Recall that for small h in radians, sine h approximates to h itself and cos h approximates to 1 minus h squared over 2. So therefore, the limit as h shrinks to 0 of sine h over h, that becomes 1, and also the limit as h approaches 0 of cos h minus 1 over h, which is equivalent to this limit and this one here, that will shrink down to 0. We must aim to isolate these limits here in these 2 bullet points explicitly when differentiating both sin𝑥 and cos𝑥 from first principles. So we need to isolate these terms and make a point of these in establishing our proofs to get full marks. So let's have a look, first of all, of how we'd differentiate sin𝑥 from first principles. Sin𝑥, the derivative of that is cos𝑥. We need to prove this. So we start off by just saying, let f of x equal sin𝑥. Then from first principles, f dashed x will be the limit as h approaches 0, fx plus h minus f of x all over h. If we sub in that f of x is sin𝑥, we then get this line here. And now we can use the double angle formulae for sine x plus h. So sine x plus h, which I'm going to highlight here in pink, using the double angle formula for that, we get it's sin x cos h plus cos x sin h minus for sin x all over h. Now at this stage here, what we can do is we can factorise out sin x's and cos x's. So if I look at the sine terms, if we factorise out a sine, we'd have cos h minus 1 all over h. So we get this limit here, and then if we factorise out the cos x, of which there's only one cos x, if we factorise that out, we have sin h all over h, so we can isolate this limit here. So the next line, we need to rewrite it in this form here, and then make a point explicitly of saying we've got this cos h minus 1 over h limit, and sin h over h as well, which we can use to our advantage. So as h approaches 0, we now say cos h minus 1 over h goes to 0, and sin h over h approaches 1. So therefore, this limit here, cos h minus 1 over h, we can place with 0 in the absolute limit, as h goes to 0, and sin h over h in the ultimate limit becomes 1. So this limit here becomes 0 multiplied by sin h, 0 multiplied by sin x, plus 1 multiplied by cos x. This is obviously nothing, so we just end up with simply cosine x. Therefore, to conclude, if f of x is sin x, the derivative function of that is cos x. Same idea, worked example 1b, prove from first principles that the derivative of cos x is minus sin x. We start in almost exactly the same way. We now let f of x be cosine x. Then from first principles, we have f dashed of x is the limit as h approaches 0, f x plus h minus f of x all over h. If we input that f of x is cosine of x, we now have this line, and again we can use the double angle formula for cos x plus h. So I'm going to replace cos x plus h with its compound angle equivalent, which is this here. Cos x plus h is cos x cos h minus sin x sin h minus the cos x over h. We now factorise out the cosine x and the sin x to isolate these two limits again, very much in the same way as worked example 1a. We next get this line here. So we've got these two limits again, cos h minus 1 over h and sin h over h. So we now need to just comment briefly on these as h approaches 0. As h goes towards 0, this green limit here approaches nothing, and this yellow limit, sin h over h, approaches 1. So therefore, this limit here, as h goes towards 0, cos h minus 1 over h shrinks to 0, and sin h over h becomes 1. So we get 0 multiplied by cos x, which is 0. Then we get minus 1 multiplied by sin x, which is obviously just minus sin x. Therefore, to conclude, we can say if f of x is cosine of x, then f dashed of x equals minus sin x. We're also going to see as well, we'll see and prove later in this chapter using the chain rule that these following results hold true. So if y equals sine kx, where k is just some constant, then if we take the derivative, that k just comes to the front of the sine function and sine goes to cos. So dy by dx becomes k cos kx. And as well, if y equals cosine k of x, again that k comes to the front, cosine differentiates to minus sine, so when we get minus k sine kx for that one. Now let's apply this to some worked examples. So, first worked example. Find dy by dx for the following, when first of all y equals sine 6x. So just to remind us of what we had from before, which was this, we can now use this result to work out part A. So part A, dy by dx, using this result here, that constant just comes to the front and sine goes to cos. The constant is 6, so the 6 comes to the front, sine differentiates to cos, so we just have 6 cos 6x. Simple as it comes. For B, cos, if we differentiate this, cosine goes to negative sine, and the constant comes to the front. And so that third is going to come to the front, So we get minus 1/3, and cosine differentiates to sine, so we get minus 1/3 sine 1/3 x. Then for c, if we notice c, it's not in the form where y is a subject. So what I'm going to do first of all is just rearrange this. So if I subtract 4 cos 3x from both sides of this, then what I will have is that 2y equals sine 20x minus 4 cos 3x. Then need to divide both sides by 2, so y is a subject, and then we can differentiate as normal. So therefore y equals a half of sine 20x. Half of 4 is 2, so we get 2 cos 3x. We can now differentiate this. So now we get dy by dx. Half is a constant, I'll leave that half as it is. Now sine 20x, sine differentiates to cos, and any constant comes to the front. So that 20 is going to come to the front of the sine function. So we then get 20, sine goes to cos. That minus 2 is a constant, so I'll leave that as it is. And then cos 3x will differentiate, that 3 comes to the front, and the sign is switched. So we then get minus 3, and cos goes to sine 3x. So we can then simplify this down to a better form. So a half times 20 is obviously just 10, so we have 10 cos 20x. Minus 2 times minus 3 is, of course, positive 6, so we have plus 6 sine 3x. So a bit of rearranging, and it's very much the same as A and B. So that's question 1 complete. Let's have a look at worked example 2. Worked example 2. We have a curve with equation y equals a half x minus cos of 2x, and we need to find the stationary points on this curve in the interval from 0 to pi for x. So stationary points, we should be thinking of the gradient function. A stationary point is when the gradient is 0. So we need to differentiate and then set the derivative function equal to 0. So if this is y, then dy by dx, if we differentiate each term respectively in terms of x, half x becomes a half. Cos, we need to remember, differentiates to minus sine, and then the constant comes to the front. And so minus, pardon me, minus cos 2x becomes minus 2 sine 2x. So in other words, we just have positive 2 sine 2x. And then we set this equal to 0 at stationary points. So we just solve this trig equation. So then we have 2 sine 2x. If this is equal to 0, if we subtract half from both sides, then 2 sine 2x needs to equal minus a half. Divide both sides by 2. Sine 2x needs to be minus a quarter. Now what I'm going to do, which you'll know from previous videos if you followed this, I'm going to replace the 2x with big X. So let big X equal 2x. I'm just going to double, x is basically double 2x. So if this is the limit for little x, if big X is double that, then these boundaries are also doubled. So 0 times 2 is 0, pi times 2 is 2 pi. So basically sine big X equals minus a quarter, because I've replaced the 2x's with just one big X. Then I'll return to the little x in a second. So now we can just work out on our calculator what the principal value is. So therefore, principal value, big X equals sine minus 1 of minus a quarter. And let's see what that gives us. So shift sine minus 1 minus a quarter. We get here a value of, I'm going to give this to 4 decimal places, and I can simplify it afterwards, because this is in terms of big X, not the little x we're actually wanting. It's minus 0.2527. Essentially. So that's the principal value of it. So now we need to think about other potential values in this limit. So what I'm going to do here is use the good old CAS diagram, like so. I've got that minus 0.2526. I should have really said it's 27 at the end because that's 6. Next to it is an 8. But hopefully you'll forgive that and know what I'm talking about, really. So anyway, from 0 to pi, I want big X to be in between 0 and 2 pi. This is the wrong way round. Sine of big X is negative, and so in which quadrants am I looking at sine to be in if it's a negative? Well, it could be in the T quadrant here, and the other place is down here in the C quadrant, although because our lower bound is 0, to get to C, we can't go the negative way round. We need to go this way. And so this angle here, it's almost a full circle. This angle is actually 2 pi, almost a full circle, apart from this 0.2526. So 2 pi minus 0.2526, and so on and so on. This angle here, because that's a negative, so 2 pi plus that answer, because that answer was negative, so it's the same difference. I get 6.0305. Just double check I've copied that down correctly. Yes, I have. So that's that angle there. Or to get to the T quadrant, I'd have to go this way round. That's pi plus another one of those 0.2526s. So this angle here, that's going to be pi plus 0.2526. Remember, all the acute angles are all going to be 0.2526 here, here, there, and there. So pi plus 0.2526, that's going to give us a value of, let's just see in a second. So shift pi plus 0.2526, or 0.25268-ish it was, 3.3943. 3.3943. So therefore, the values of big X, which are in the range from 0 to 2 pi, we've got here 3.3943 radians, or the one in red, going almost all the way around the circle, 6.0305. But because big X is double what little x is, we need to go to our original variable, which is x, and just divide these two values by 2. That's how we get our solutions. And so our values, x is going to be 3.3934 divided by 2. So to three significant figures, I'm going to call this one 1.70, because 697 would round up to 70. So x is 1.70 for this one. And then for the second one, 6.0305 divided by 2. That's what that gives us. To three significant figures, we'll call that 3.02. So those are two values of x. So in terms of from 0 to pi, x can be 1.70 radians or 3.02 radians. So let's have a look at a final worked example number 3. So here we've got a curve of equation y equals 3 sine 2x plus 4 cos 3x. And now we need to show that the equation of a normal to the curve at the point when x equals pi over 2 is given by 2x plus 12y minus pi equals 0. So again, what we need to do is differentiate with respect to x. So dy by dx, sine goes to cos, so we've got 3 lots, but then sine goes to cos and the constant comes to the front, so that becomes 2 cos 2x. and then cos differentiates to negative sine, and the constant comes to the front. So cos 3x will become minus 3 sine of 3x. Then simplifying fully, we've got 6 cos 2x here for the first term, and then 4 times minus 3 is minus 12 lots of sine 3x. So we want to think about the equation to the normal when x is pi over 2. So when x is pi over 2, we can work out the derivative at that point. So when x is pi over 2, the derivative when x is pi over 2, we can just substitute in pi over 2 in place of x. So we have 6 cos 2 lots of pi over 2, which is 6 cos pi, and then 3x will be 3 pi over 2. So we can either use our knowledge of the cosine and sine graphs, or we can just bang this into our calculator if we want to be lazy. It doesn't particularly matter which way we do it because it is a calculator exam. But if we type this in our calculator, just to make absolutely sure, we're going to get 6 cos pi minus 12 sine of 3 pi over 2, and that's going to give us a value of 6. So therefore, if that's the gradient of the tangent, the gradient of a normal will be the negative reciprocal of that. So that's going to be minus 1 over 6. So therefore, the normal equation, any straight line is of the form y equals mx plus c. So y equals mx plus c for this normal as well. However, we've just calculated the gradient of a normal at the point when x is pi over 2 needs to be minus 1/6. So therefore, the equation of a normal in the form y equals mx plus c is y equals minus 1/6 of an x plus c. But we can now substitute in when x is pi over 2. Okay, so sub in x is pi over 2 and y equals, well, what? So when y is pi over 2, let's just see what, so when x is pi over 2, let's see what y is. So y, we've got here is 3 sine 2x, so that's 3 sine pi when x is pi over 2, then plus 4 lots of cosine 3x. So when x is pi over 2, 3x will be 3 pi over 2. So we can work out what the y-coordinate is when x is pi over 2. We get y as 0. So essentially, when x is pi over 2, this is the x-axis intercept. So when x is pi over 2, y is also 0. So y, 0, x, pi over 2, so minus 1/6 times pi over 2 plus c. Minus 1/6 times pi over 2 is minus pi over 12, so therefore the equation c needs, sorry, the variable c, constant c, if I can even speak, needs to be positive pi over 12 by just rearranging this. C has to be pi over 12. So the normal, we've got y equals minus 1/6 of an x plus pi over 12, but we need to have it in this form here with no fractions. So my suggestion at this point would be to multiply both sides by 12 to undo any fractions. So if we do that, y becomes 12y. 12 times a sixth is 2, so minus a sixth times 12 is minus 2. Pi divided by 12 times 12 gives us pi. Then finally, if we get everything onto the left-hand side, so we can add 2x and take away pi from both sides, we then get the result we need. So therefore, adding 2x to both sides, we get 2x. The 12y was already on the left-hand side, minus a pi, and on this right-hand side we now have 0, and that is exactly what we needed to prove. So the equation of the normal is 2x plus 12y minus pi equals 0, which is precisely what we wanted to prove because this thing here is the same as what we needed to show in the question. So we're done. So that's all from me, and now it's up to you to try some of these on your own. So if you can turn to page 234 in the blue Year 13 main pure algebra book, exercise 9a, try all the questions, go now. So each time you do a couple of questions, do check to make sure you got them right using the answers at the back of the book or by asking me or somebody in the class that you trust. And practice, practice, practice is the way to success. So thank you for listening. I hope you found some of that useful, and I hope to see you all very soon indeed. So take care of yourselves. Until next time, it's goodbye from me.